Hi everyone, this is Dr. Swaminathan SM. Now I am going to discuss about the topic transfer function in the control system modeling unit. So first, what do you mean by transfer function? That is a ratio of output divided by input. That is called the transfer function. So review about the previous class. First, we discussed about the ordinary differential equation, partial differential equation, heat equation, Laplace equation, wave equation we discussed. Next, the transfer function definition and what are the methods to find. And next to the problems and why Laplace transform is used, following with the activity applications of transfer function, poles and zeros, and bounded input, bounded output versus the transfer function, and the summary. Next, the transfer function already I told. U of t, that is planned input, and y of t is the planned output. So the transfer function is the ratio of Laplace transform of the output to the Laplace transform of the input. That is called the transfer function. So if L of u of t is equal to u of s, so the Laplace transform is time domain is converted into s domain. So L of y of t is equal to y of s. So g of t is equal to c of t divided by r of t. And next, input system input is r of t, g of t is c of t divided by r of t, and the output is c of t, input is r of t. In terms of Laplace transform, we will discuss about the inputs. It is r of s, and the system g of s. The output will be the c of s in terms of Laplace transform. So g of s equal to c of s divided by r of s. So the transfer function g of s, that is L of c of t divided by L of r of t. L of means Laplace transform of. So the initial conditions equal to 0. So this is called the transfer function. So g of s, that is y of s, output divided by u of s is the input. So how can you differentiate the v of I of t is equal to ri of t plus 1 by c I of t into dt. V naught of t, that is equal to ri of t, the Laplace transform ri of s plus 1 by cs into I of s. Ri of t is converted into ri of s. So next, the V naught of S, output divided by input R by R plus 1 by CS. So next, V naught of S divided by Vi of S is called transfer function. So here this is the wave, that is a circuit. We will use Vi of t, C is the capacitor, R is the resistor. So the RC circuits, the input current is I of t, V naught of t is equal to output voltage. So here this is the another example for transfer function V naught of S. So here this is the V naught of S, R1 R2 C. So first VI of t is equal to R1 I of t plus R2 I of t, because both are series connection. If series means added, plus 1 by C integral part of I of t into dt. So because C will come means that is a definition, 1 by C integral part of current into dt. Resistor means R into I, because V is equal to IR. So V is equal to IR means that is R1 is the first resistor. I of t is the current. So V is equal to IR formula. That's all. So if in terms of capacitor, suppose if they are given, the voltage means 1 by C integral part of current into dt. That is a common function. So again, the V naught of t is equal to R2 of t, that is the output side. That is the two loops we are having. The first loop, that is Vi of t, and the second loop, that is called V naught of t. So V naught of t, that second loop consists R2C. So R2 into I of t plus 1 by C integral part of I of t into dt. The next we will apply the Laplace transform. Again the Laplace transform will comes. So why you are using the Laplace transform? Any common function, L sine of t is equal to omega by s square plus the omega square. L into e of minus at means 1 by s plus a. So s is equal to sigma plus j omega, that is the complex form. So the mostly derivatives, that is we are using the L dx of t divided by dt, that is s into x of s minus x of 0. And dt squared means, that is we need to substitute the s squared x of s minus s into x of 0. So minus dx of 0 by dt. So here these are all the Laplace transforms. So Laplace transforms in terms of general forms, dn x of t divided by dt power n equal to Sn x of s minus summation of k is equal to 1 to n Sn minus k x of k minus 1. That is the first. And again that Laplace transform derivations, we will use the L x of t into dt, 1 by s into x of s. So the transfer functions auxiliary forms ax double dash is equal to cy dash and minus bx dash dt. That is taking the Laplace transform in the both side. We will discuss about the a into s squared x of s minus s into x of 0 minus x dash of 0 is equal to c into again the y term again minus b into that term. So you just substitute both side of the Laplace transform. So the calculation of the transfer function, we will use a s squared of x of s equal to c into s y of s minus b s x of s. So again the rearrangement, we will use x of s in left hand side and y of s is the right hand side. Then you can use the partial differential equation. Following with this activity, tell about yourself. That is the first questions asked by the interviewer. So please be clear about this activity. And again the transfer function, we will use y of s divided by x of s. Y of s is b term and x of s is the a naught term. Transfer function we are use x of s divided by, that is y of s divided by x of s. So that is it's a proper, that is a greater than the when the order of the denominator polynomial, that is the denominator polynomial is greater than numerator means proper, otherwise it is improper. Applications means stability and the time domain, frequency domain we finalize, and the response of the any system given input, and absolute stability, relative stability, everything is we will use for the poles and zeros we discussed. If the denominator is equal to 0, then you can find the pole. If the numerator is equal to 0, then you can find the zeros. And the same thing for poles of the system that represent x and 0, that is represented by the 0, and otherwise the order is equal to the number of poles. And next following with the nth order, and b naught s m, b naught is increased b1 b2 up to bm minus 1 plus bm, and s is degrees, that s numerator, that is s order sm minus 1 up to s into s naught. S naught means that is s1. The same term for x of s. So the stability of the system, that is 0, is the frequency when the system becomes 0. And again the stability of the system, that is defined, pole is also defined, the frequency at which the system becomes infinite, like a magnetic pole or black hole. So this is the relation between the poles and zeros in the single pole system. And following the example, x of s divided by y of s, c divided by as plus b. So the denominator polynomial equal to 0 means s is equal to minus b by a. And examples, there are different examples we are using, 4 examples. And left half plane and right half plane, if the s plane is having, and the x axis is sigma and y axis is the j omega. So s is equal to sigma plus j omega. How can you find the stability of the system? Means all the poles of the system, left half plane means that is left hand side means stable, right hand side means unstable. If poles on imaginary axis means that is marginally stable. So stable, unstable or marginally stable, these are all the important point for the stability of the system based on the poles. And again the g of s, that is c divided by as plus b, a, b, c values are given, and again you can get minus 3 and poles equal to minus 3. So if minus 3 means what? That is negative side. And next is the other definition of the stability, bounded input, bounded output. That is, if the system is stable, then you can say the bounded input and bounded output. That is, for example, unit step input means that is 1, that the output range is 1 u of t, and the unstable means that is the other one. Other definitions for unstable, that is stability means unit step input, that is unstable means bounded input and output is not bounded, that is mean unstable. So poles and zeros, you can find the g of s, the transfer function is given, there is 2 differential equations. If numerator is equal to 0, Then it is called poles. That is, poles means denominator equal to 0. So 7 is known as a gain factor, that is denoted by k. That is poles and zeros. So the poles zeros diagram, number of poles equal to number of zeros, that is called the that is in above examples, that is 0 zeros, s equal to infinitive. So you can say, so look at this, 0 minus 3, the poles and zeros, everything is noted. So look at this, the poles and zeros are noted. So you can say example of the y of s divided by u of s equal to 1 by s plus 3, and g2 of s is equal to y of s divided by u of s, that is 1 divided by s minus 3. You can get the different output values of the functions. For example, you can get the Laplace transform function. From this Laplace transform function, you can draw the e power minus ut, e power minus 3t u of t, and e power 3t u of t. That is two different waveforms you can get. So in this functions, we will discuss about the transfer function, the order of the control system, poles, zeros, and stability, bounded input and bounded output. These are all the topics we discussed in this units. Thank you.